So coming from ExxonMobil, we've got Ashish Mhadeshwar, um, developing technology solutions for low carbon hydrogen.
Thanks for the introduction and thanks for the opportunity to present here. I work in ExxonMobil Low Carbon Solutions hydrogen technology portfolio, which is part of our technology and engineering organization. Today I'm going to talk about the role of hydrogen in energy transition, specifically why ExxonMobil is working in certain areas. I'll talk about some innovative and emerging technologies in the field of blue hydrogen. And then I'll also highlight some R&D collaborations that we are pursuing with UT Austin. I hope the font is large enough for all of you to read. Otherwise, I'm going to spend the next 10 minutes to go over the details. But jokes aside, what this means is that you should not make any financial decisions based on what I tell you today. This slide has nothing to do with hydrogen, but I have fond memories working with UT Austin Energy Center for 3 years, back in 2018 to 2021. I was working with Professor Vaibhav Bahadur and his group in mechanical engineering. And we were exploring if CO2 can be rapidly converted into CO2 hydrates at high pressure and low temperature conditions. VB's group came up with some really innovative ideas of using surfaces like aluminum and magnesium to promote the nucleation and growth of these hydrates. And let me see if I can play this video. So this video shows how water droplets placed on aluminum plates can rapidly convert into CO2 hydrates in a CO2 rich environment of high pressure and low temperature. We did a lot of interesting experiments like these, and I strongly believe that fundamental science-based industry-academia collaborations are absolutely important when you are trying to evaluate emerging concepts and ideas. Back to hydrogen. At ExxonMobil, we strongly believe in developing technological solutions that are grounded in fundamental science. And that's really important as we work on the dual challenge. So the dual challenge has two components. First is we need to meet the world's growing demand for affordable energy and essential products. And the second thing is we have to do that while reducing the environmental impact and emissions. If you look at the total emissions every year, the world generates around 34 billion metric tons of energy-related CO2 emissions every year. Only 10% of those emissions come from light-duty transportation. On the other hand, industrial activities, commercial transportation, these contribute around 80% of the emissions. And these are hard to decarbonize sectors. So developing emissions reduction technologies in these hard to decarbonize sectors presents a huge opportunity. It's around a $6 trillion opportunity. At ExxonMobil, we develop decarbonization technology solutions that are based on our current capabilities. And we are working on commercially viable solutions like CCS, hydrogen, biofuels. So I want to take a moment and talk about why we work in these three particular areas. At ExxonMobil, our core expertise is in molecule management, especially if those molecules contain carbon and hydrogen atoms. We work on technologies where we know how to capture these molecules, we know how to convert these molecules, we know how to transport these molecules and store these molecules. So we work in these technologies that are molecule-based because this is where we think that we can bring unique and important capabilities. At the same time, it's important to recognize that all technologies are important. right? Whether they're molecule-based, like CCS, hydrogen, biofuels, or electron-based, like wind, solar, nuclear, and so on. Applications of these three technologies, CCS, hydrogen, and biofuels, are expected to grow significantly over the next 25 years. If you look at the middle chart that focuses on low-carbon hydrogen, we anticipate that hydrogen will be important in two important sectors: industrial activities and commercial transportation. Hydrogen is expected to play a key role in replacing the traditional furnace fuel, and hydrogen will reduce emissions when it's used in commercial transportation over long term. We have heard about a lot of colors, but I'm still going to use this slide to talk about colors of hydrogen because I want to tell you why Exxon is working in certain areas. So I'm showing you 5 colors of hydrogen here, and there are more colors that are not shown. When you make hydrogen using your traditional reforming, it's referred to as gray hydrogen. When you combine that reforming with CCS, now you are making blue hydrogen. If you do methane pyrolysis, where you convert methane into carbon and hydrogen, then that hydrogen is turquoise hydrogen. If you do water electrolysis with nuclear power, it's pink hydrogen. And if you use renewable power, then it's green hydrogen. But at ExxonMobil, we know how to work with natural gas. Our expertise is in natural gas processing. And so we are working in blue hydrogen and turquoise hydrogen. Technology for converting natural gas into hydrogen exists, and it exists at industrial scale today. When you combine that with CCS, you make low carbon hydrogen or blue hydrogen. And making blue hydrogen is the most cost-effective method so far out of all the colors of hydrogen shown here, except for gray, but that doesn't have CCS. So blue hydrogen is highly scalable, and it's highly cost-effective. And that's why ExxonMobil is working in that area. Methane pyrolysis is an emerging technology. It's very interesting, attractive technology for areas which are challenged for CCS. Methane pyrolysis is unique because it has 2 co-products. First is low carbon hydrogen, and second is solid carbon. So transporting and storing solid carbon may be more cost effective than transporting and storing CO2. Methane pyrolysis also takes advantage of the existing global LNG infrastructure, so we can provide methane at scale. So scaling this technology, scaling methane pyrolysis, aligns with our core capabilities and also our operational experience. And that's why ExxonMobil is interested in exploring turquoise hydrogen or methane pyrolysis. Again, I'll reiterate, all technologies are important, all solutions are important, and the cost of all these technologies is going to come down over time. But at this point, our view is that blue hydrogen seems to be the most cost-effective method for low-carbon hydrogen production. And this is why we are working on developing the world's largest hydrogen production facility in Baytown. This facility can potentially make 1 billion cubic feet of low-carbon hydrogen per day. That's a lot of hydrogen. That's equivalent to providing power to 1.5 million homes. This facility can produce up to 1 million metric tons of low-carbon ammonia per year. Around 98% of the CO2 that is generated by this facility will be captured and stored over long term. That's 7.5 million metric tons of CO2. That's a lot of CO2. That's equivalent to removing emissions from 1.5 million cars. So this facility will make low carbon hydrogen or blue hydrogen for us and also for our customers. And so it will have positive impact on reducing the greenhouse gas emissions. Part of the hydrogen will be used in our own facility, so that will help us in decreasing the scope 1 and scope 2 emissions. And it will also allow us to make products with lower carbon intensity. We have made strategic investments that give us access to differentiated low-cost natural gas that is very important in hydrogen production. We have access to the largest CO2 pipeline in the US, and we have access to pore space where we can store all this captured CO2 for a very long time. So we are very excited about the Baytown project. But as we work towards the net zero ambitions of society, I think we have to do more, and that requires unlocking the broader hydrogen market. And that requires two things. You need policy support and growing market incentives. And the second thing is you need to decrease the cost of blue hydrogen production. Blue hydrogen is a cost-effective technology, but it is still expensive. We need to decrease the cost. You can decrease the cost to some extent by playing with the scale of the technology. But cost can also be decreased through technical innovation. And this is why at ExxonMobil we are looking at a variety of technological solutions that could help in decreasing the cost of blue hydrogen production. We have been looking at technologies across the whole TRL spectrum. And there are some low TRL or early TRL ideas, concepts that are emerging that look interesting for decreasing the cost of blue hydrogen. And so on the next slide, I'll give you a couple of examples of those upcoming blue hydrogen technologies, ideas. But they have technical challenges associated with those ideas. And this is where academia can play an important role by working on those challenges so that the concepts can be moved from low TRL to high TRL. Before I give you the examples of the emerging ideas in blue hydrogen, I want to talk about the current baseline process, ATR-based hydrogen production to make blue hydrogen. This process has a lot of steps. It's a complicated process. It has a lot of equipment. You start with the air separation unit that gives you oxygen for the ATR. You need the main autothermal reforming reactor that converts natural gas into syngas. Then you need the water gas shift that takes the syngas and shifts the composition to make more hydrogen. And then finally, you need downstream separations. You need the hydrogen PSA, pressure swing adsorption, to get a clean stream of hydrogen. And you need a CO2 capture unit. That could be amine-based unit or a cryogenic unit. That's a lot of equipment. That's a lot of CapEx. And so one may think that majority of the cost comes from chemistry or reactions. But in reality, downstream separations are quite expensive. And this is why ideas that can reduce the downstream separations or even eliminate the downstream separations can have impact in decreasing the cost of blue hydrogen production. Second thing is that if you look at the ATR and water gas shift reactors, they are highly optimized reactors and they're operating close to equilibrium. So any ideas that can overcome those equilibrium limitations can reduce the downstream separations, and in turn, they will have an impact on decreasing the cost of blue hydrogen. So I'm going to show you 3 examples that operate on those guiding principles. The first one is chemical looping. The idea of chemical looping is that you split the methane reforming chemistry across multiple reactors, and hot metal oxides are circulated across these multiple reactors. In those multiple reactors, basically the metal oxide is undergoing different type of reaction, and it has a different oxidation state. So in the first reactor called reducer, you provide methane, and it reacts with metal oxide and gets completely oxidized to CO2 and steam. If you condense out steam, you have access to pure CO2. That's your first product. In the second reactor called oxidizer, you provide steam as the feed that reacts with metal, and now you make hydrogen. If you condense out steam, then you have access to hydrogen stream. That's your main product. And in the third reactor, which is the combustor, you provide air as the feed that oxidizes the metal back to metal oxide, and what comes out is oxygen depleted air. So what's interesting and unique about this chemical looping concept is that it is making the two products in two separate reactors. One reactor is making CO2, other reactor is making hydrogen. And that means you don't need downstream separations, right? But of course, there are technical challenges. You're moving hot solids across multiple reactors. They will undergo attrition. They will have stability issues, reactivity challenges. Scale-up will be challenging. And so that's why R&D will be required to move the concept from low TRL to high TRL. Second idea is sorbent-enhanced water gas shift. So here the principle is to shift the equilibrium for the water gas shift reaction. Typically, water gas shift has two reactors, a high temperature shift followed by a low temperature shift or a medium temperature shift. And there is an intermediate cooler. This idea replaces all that. It's basically a hot PSA integrated with water gas shift. So the bed consists of water gas shift catalyst, but it also consists of sorbent that is selective to CO2 adsorption. So as the syngas from the ATR is sent over this unit, that syngas is getting shifted because of the water gas shift catalyst. But the CO2 molecules are selectively adsorbed on the sorbent. So what comes out is a hydrogen-rich stream. After some time, the sorbent will be full of CO2, so you have to take the bed offline, and you have to regenerate that, and then you'll get access to pure CO2 stream. So again, the unique thing about this concept is that you're making your two products at two different times. In one duration, you're making hydrogen, and subsequently, you're making CO2. So there is potential to decrease the need for downstream separations. But again, the technical challenge is that typically you do PSA at low temperature, like 40 degrees Celsius. And now here we expect CO2 to adsorb at hot conditions of water gas shift, 300, 400 degrees Celsius. So again, R&D is needed to move the concept from low TRL to high TRL. And the third interesting emerging idea is sorbent-enhanced SMR. So the principle is the same as the sorbent-enhanced water gas shift, but the reaction is different. It's steam methane reforming. So here, the first reactor has the SMR catalyst, and it also has a fresh feed of sorbent, as a feed of fresh sorbent. And that sorbent is selective to CO2 reaction. So what happens is that when you feed methane, and as the SMR reaction is going on, CO2 molecules selectively react with that sorbent and make carbonate. What comes out is a hydrogen-rich stream. And the spent sorbent is moved to the regenerator, where you can provide heat, and now you can basically recover the CO2. So again, the unique feature, you can get the common theme here. The unique feature is that one reactor is making CO2 and other reactor is making hydrogen. The technical challenge is that you basically are moving hot solids, so same as chemical looping, right? There will be attrition, there will be stability challenges. You need to provide heat for regeneration, and that heat itself will be associated with CO2 production. And so that CO2 has to be captured. So these are all really exciting ideas, but they are low TRL. And this is where I think moving from low TRL to high TRL is going to need collaboration with academia, industry, and national labs. This brings me to the last part of my presentation. I want to quickly highlight a couple of R&D projects that we have ongoing with UT Austin. They are in the area of hydrogen sensing and emissions quantification, and also in hydrogen blending with natural gas for residential applications. So we always think about methane emissions and CO2 emissions, but we have to think about hydrogen emissions too, because we are working more and more in the field of hydrogen. Now, the primary mechanism by which hydrogen indirectly influences the climate is generally well understood. Hydrogen reacts with molecules like hydroxyl radicals, which would otherwise have reacted with methane to break down methane. So hydrogen is not a greenhouse gas, but it's a short-lived climate forcer. But detection of hydrogen is very challenging. Unlike methane, hydrogen detection is sniff, not see. With methane, you can do remote sensing over large areas, but hydrogen is not IR active. So detection becomes very, very challenging. So in this area, we are collaborating with Professor Michael Lewis, and with UT Austin, we have modified the hydrogen at scale facility to include this controlled release of hydrogen capability. And so at this facility, now sensor developers can go and test their measurement technology in a facility that's more complicated than a lab, but less complicated than a large manufacturing facility. But we are very excited about this collaboration. Sorry. The second collaboration we have is in the area of hydrogen blending with natural gas for residential applications. In future, hydrogen may play a role in residential applications. You can imagine that it could be used in furnaces, water heating, or cooking application. Now, we know that when natural gas is used in cooking, it creates NOx emissions, particulate matter emissions. The question is, what happens to those emissions when you blend hydrogen with natural gas? To address this question, you need a facility that's well equipped with sensors, and you need a dedicated facility. And so what's amazing about the UT Austin facility is that there is a multi-room house that is equipped with these sensors, and it is dedicated to full-scale indoor air quality research. This is a collaboration with Professor Leah Hildebrandt Ruiz and Professor Attila Novoselac, and the team is looking at what happens to the emissions when you blend different ratios of hydrogen and natural gas, what happens if you use a stove versus an oven, what happens if you use a pot, what happens if you cook with real food, and so on. These are really important collaborations for us, especially when we look at addressing questions, long-term questions about hydrogen. The last thing I want to talk about is natural hydrogen. Very quick remarks. Through our participation in the GeoH2 consortium, we are monitoring the activities in the natural hydrogen space. We have heard a lot about natural hydrogen. It is generally produced through radiolysis and oxidation, but hydrogen is a light molecule which likes to escape. It diffuses through rocks. It escapes through faults and fractures. Microbes like to consume it. And so if any hydrogen survives, you need a tightly sealing cap rock for sufficient accumulation. And so far we have not seen sufficient accumulation with high purity, but I really hope that the idea works. So overall, the message I want to give you is that ExxonMobil is fully committed to low carbon hydrogen. We are working on technologies across the whole TRL spectrum. We are working on high TRL mature technologies. We are exploring low TRL emerging ideas. And we really value the collaboration with the universities, national labs, and industrial partners. These are a couple of reports that we have published this year. The first one is the Global Outlook that talks about our perspective on what could happen in the next 25 years. And the second one is a progress report on what we have been doing in advancing climate solutions. Thank you so much for your time. I'll be happy to take, I don't know.
All right, Mike was really quick to give me a question. How can blue hydrogen ever compete against natural gas with those hard-to-abate sectors when you make the hydrogen from natural gas?
How can it ever be cheaper than natural gas?
It will, yeah, yeah, no, hydrogen, okay, natural gas will be cheaper, always, right? But if we really need to move towards decreasing the emissions for the society, we have to use low carbon hydrogen. And you have to pay, first of all, originally I thought the question was about gray hydrogen versus blue hydrogen. As you convert natural gas to gray hydrogen, let's say, gray is more expensive than natural gas. And as you put CCS behind that, blue hydrogen is even more expensive, right? But as we go towards the net zero ambitions of the society, we have to start using low carbon solutions. Yeah.
Exxon has not yet announced FID for the Baytown project. What further confidence do you need to make FID?
So the final investment decision is subject to policy and stakeholder support, regulatory approval, and market conditions. And I know that the 45V rule has now updated the startup of the hydrogen project's construction from 2033 to, I think, early 2028. But we are confident that our project can meet that deadline.
All right, I think we're ready for a break. Let's thank the speaker again. That was great.
Thank you.